Remember the parallelogram rule? Do you remember that? We're not doing it. We're gonna do the mathematical way only. So what's the way to find a resultant when you have a whole bunch of forces? Add them all together, right? So pulling Chris this way, I'm pulling Chris this way. Wait, go back a little bit. I'm pulling him this way, pulling him this way, but in the end, the resultant is he coming right to me. Right? So that's all I have to do is take the x's, x, add them together, add the y's, z's. Okay, so let's look on the other side. I can't tell if mine's original or not. Okay, so we have the two forces up on the top. How are they represented there? How are F1 and F2 represented? Vector form. So we have, and some of you might like this instead. Can you see? Yeah. 64.9, 162.2, negative 97.3 counts. Some of you might not like to put pluses in and might not like to put the I, J, and K. You can do it this way. This is totally fine. But remember to use these triangular brackets and put commas between. And still remember to put units at the end. So we're going to add up the x's, add up the y's, and we get the resultant. And we get the resultant here in vector form. Notice still one decimal place, right? So how would I find the magnitude of that resultant? How do I find this magnitude? Pythagorean theorem, right? X squared, y squared, z squared under the radical, and I get 343.9. So in this case, when you're trying to find resultants, how did we represent it here? Vector form. So we represent resultants in vector form. And the other way of representing resultants is magnitude and direction angles. What do I mean by direction angles? Theta x, theta y, theta z. We don't represent resultants using unit vectors. These are the two ways that you represent resultants. Remember that? Okay. So that means that I need to find the direction angles. So the direction angles are the inverse cosine of Rx, the x component over R, the y component, the z component. And we'll talk about cosine in a little bit. Right? Just to show you the opposite, couldn't I have said Rx is equal to R times the cosine of theta x? Does everybody agree on that? If I want to find the x component of the force, I multiply the force times the cosine of theta x. So now, are there checks here I could do? I have three angles, right? Can't I do the Pythagorean's check, Pythagorean theorem's check? And I checked it. And I could also do a positive visual, or we could call it acute obtuse. Which of the direction angles gave me an obtuse value? Theta x, right? So that means, what should that mean about the resultant in the x? It should be negative. And is it negative?
Yes.
Yes. And then theta y and theta z were acute, right? Less than 90. So what does that mean about the force directions? Positive. And are they positive? Yes. So we check that as well. So for resultants, you sum up the x's, sum up the y's, sum up the z's, represented in vector form, represented in magnitude and direction angle, which means you have to solve for the direction angle. You do a check, and you check positive and negative. So this is exactly how I want you to see, I want to see any kind of components. I remember in physics, when you're given forces, if you're given a force, you say, Fx is this, Fy is this, Fz is this. So if you have force 1, force 2, force 3, you find 1, you find 2. This is 2 much time wasted on setting up little things. In physics, it's totally cool because you're doing simple problems. You only, not all physics is simple, but the statics problems you did in physics were only 2D problems, and they were all angle problems. You never did a ratio problem, you didn't do any 3D problems, so you did problems that weren't that complex. So it was totally fine spending all that time writing all the components down. You know, Rx is equal to Fx1 plus Fx2 plus. Don't do it like this. We are going to do it in 3 steps, so it's methodical and it's quick. So setting up the forces, 3-step process, right? So you're representing the magnitude and the direction, whether you have angles or distances, then you magnitude and unit vector, and then the Cartesian vector form, and then do all your checks as you go along. Because if you do a check and you know you got it wrong, you can correct it right then, rather than going through the whole problem and then doing the check and finding out you made a mistake on the math. And then again, for resultants, important to represent it in vector form and magnitude and direction angle. And I will always tell you how I want something represented. Okay, everybody stand up. How many of you took materials last semester? Remember tension? I don't think you can really do compression. Bending? Torsion? And you can't really shear the top half of your body. Okay, tongue down. Okay, so I need hands high. Who took materials last semester?
Or the semester before?
Okay, who already took materials? Okay, who is in circuits or took circuits? Okay, who's in math 6? That's usually the lowest. Who's in math 7? Who's in physics 4C?
Yeah.
Wow.
So it usually works out to be half material, you know, it's somewhere between 1/3 and 2/3. So that's 1/3, a half, and 2/3 of you taking materials. Then some physics 4C. Math 6 usually not too many. And then, so math 6 is right before this class, right?
Yep. It was right before this class.
It is, because I told them when to teach it. and math 7 is right before circuits,
Yeah.
right? So does that mean that almost all of you are free right before my class?
No.
Who is free right before my class? What are you taking? Are you taking math 5C? Communications. Okay. So if you ever have questions, I'm here early. You could come in. But sometimes I'm a little frazzled right before class, so I might have to say no. But okay, let's go back to all the summary. We already did the vector summary. We already did the check summary. We're going to look at cosines in a little bit. You know this already. You had to do a lot of free body diagrams in the physics. The new thing is you're doing a lot of 3D free body diagrams. So you have to get comfortable drawing in 3D, seeing things in 3D and drawing in 3D. Who took graphics? Okay. So in graphics, you guys were, you got more comfortable seeing things and drawing things in 3D. So those of you who haven't taken graphics yet, anybody in graphics now? Okay. So that's just going to be maybe a little bit more of a challenge. So remember, on free body diagrams, you always label the positive end of the X, Y, and Z axis. Always label it. You could take the axis I give it and you could totally turn it around. You can tell me whatever axis you want. You just have to make sure I know what axis you're using. Always draw free body diagrams. Also, you always need your force labeled. The force needs to be labeled either with a variable like F1 or whatever the magnitude is given. But you always need forces labeled. And then you need directions shown. So that means either angles or lengths to get ratios. Because all forces are vectors, you need to show me the magnitude and the direction, okay, of all forces on a free body diagram. We looked at all these rules already. Let's look at this. These are just summaries from homework 1 and 2. We already looked at free body diagrams. When you represent a force in vector form, make sure you put on units. Make sure the force has 1 decimal place more than given. And make sure that you report the I, J, and K, or those brackets with commas. If you represent a force in magnitude and unit vector, the unit vector is always 4 decimal places and always represent the units of the force. Checks. Always do a positive and negative visual check. Always do a force magnitude check. Always do a unit vector check. And then when you represent your force in magnitude and direction angle, make sure you have your units on your force, and make sure the direction angles are 1 decimal place. So this sheet, this summary sheet, this is basically kind of like a review of what you've done, a review of what we've done today that shows you all the rules. How many decimal places on unit vectors? How many decimal places on direction angles? How many decimal places on forces?
One more than
One more that's given. Do you always show units? Yes. Whenever you represent a variable and you put an equal sign, you have to put units. I have seen that maybe sometimes you carry units and only put it at the bottom. You can't just put it at the bottom. If you say F1 is equal to, I'm going to write with Sharpie. It's not a good idea. If you say F1 is equal to something, you have to put the units here. You can't just assume this is scrap paper and then at the bottom you write units. Whenever you represent a variable with an equal sign, you give me what?
units.
When you represent a variable with a unit sign, you give me units, always. Question, Jose? Oh, I thought you did. Oh, will they?
Yeah, just talking about units. I mean, like in the field, when you work as an engineer, are we gonna be working with SI units or just
Both. Both. So science, and you know this already because you came through chemistry and physics, science converted. I mean, when you're doing experiments, scientific experiments, typically you're using metric system. And a lot of it came from, Germany and mostly Germany. So you're going to be using SI, but in engineering, you're going to be using both. There was a time where, well, actually, when I was in first grade, which was a very long time ago now, I remember them saying we were going to switch. Well, we still haven't switched, right? On plans, typically you have to represent both, of course, if you're working with a company that's global. But you use both. So you're going to find in statics we're using both units. And that's what you did in materials too, use both units. Civils still pretty much use English, but they represent metric on their plans. But they really talk in English. Okay. Use of cosine. Let's talk about cosine now. I have an example. I do have that, also was in surveying. Today, that surveying example. Be right back.